Okay, welcome back from lunch from UCLA. The next session is about software-defined networking, which is an exciting topic that many people in industry and academia are interested in, where the idea is to basically replace the low-level router network behavior with higher-level programs and things that we understand and know how to do. Good fit for our community. A lot of interesting work happening, and 3 interesting papers today. Will be Jed McClurg from University of Colorado Boulder, talking about how to do updates safely in the presence of events.
All right, thanks. So hopefully, I'm assuming. So hi everyone, I'm Jed. Today I'm going to talk about event-driven network programming. Hossein and Nate at Cornell, and my advisor Pavel at the. So in a software-defined network like this one that I have shown, we have this row of via switches in the network, and static forwarding behavior as like a particular instance of time is routed in the network, and we often refer to one of those static behaviors as a network configuration. So there are many languages which you might have heard specifying one of these static configurations. So Netcat is an example of that. And the way that these work is by basically instructing the SDN controller to program rules onto each of the switches in the network. And that defines the forwarding configuration for that moment in time. But there's a recent trend in SDN, and that is that devices are becoming more programmable. So rather than just having sort of a static set of rules on each device, you might have mutable state that can be changed, particularly state that can change in response to events, various types of events in the network. So as you might notice, there's a new problem at the writing programs for these type of dynamic networks is possibly a static case, because now we have a distributed system, and now we have to deal with things like handling state distributed nodes. So how can we do that? How can we ensure correctness as we're programming in this distributed context? So one of the ways that people have done this is which provide consistency in the form of an atomic, just like you would in have this atomic operation in the network. So hopefully executing distributed updates atomically can be expensive. So if you want to have something happen on each of these selected that happens atomically with respect to packets, some type of coordination between at least those two devices. We want to not do that in our approach. So this atomic consistency, we want some possibly weaker, but it also allows all of the programs in our approach to be so there are two pieces of our consistency. The first one is answering the question, when should we respond to events? So let's take a look at this example of a stateful firewall. So in dynamic programs, a packet event can trigger an update in the network. So here we have an example where H1 represents an internal host, say inside of a company network, and H4 represents a external host, say on the internet. So at all times, H1 can communicate with, send packets to H4, or has received an internal packet, can it communicate on the incoming path here. So the first thing to notice is that any type of consistency that we talk about involve multiple packets. Specifically, we have a packet of outgoing type influencing the future processing of packets of the incoming type. Another thing to about how we do this, there can be problems. Let's say that H1 starts at 4, and the packet arrives at switch 4, and at that point, change the network configuration. As S4 do, it notifies the SDN controller about goes ahead and forwards it to the destination. And then immediately responds to the packet. So now there's a problem because only the controller come back and install a rule that configuration. So in the interim rules on this switch S4 for the incoming packet, and it just gets dropped. So the problem here is that we need stronger guarantees about when configurations should change with respect to the events. And in particular, we don't want to respond to an event too late, as in this example, because that causes some of the packets to be dropped unnecessarily. Similarly, we don't want to respond too early. Consistency model is we need to deal with events, so events that conflict with each other. And what I mean by that is consider a different type of stateful firewall. The first contacted external host is traffic. So H1s can still talk to H4 and H5, but only the first one that's contacted will be able to respond with incoming packets. So the difference here is that switch S4 ideas of which of them was first in receiving a packet. And so you can't actually implement this type of program efficiently without some kind of possibly expensive coordination between those two. So we want to formalize exactly which of these programs and which are not. Okay, the two pieces of our consistency model. The first one is something we call event-driven consistent update. And this determines whether a packet is processed in an initial configuration or a final configuration with respect to an event. So to kind of make this formal, if all the switches traversed by a packet have heard about the event, then the packet will definitely be processed in the final configuration. Similarly, if none of the switches traversed by the packet have heard about the event, then it will be processed in the initial configuration. What remains to be seen is what it means to have heard about an event, and for that, happens before relation on packets. So this is the first piece of the puzzle. Structure consistency, and this one specifies how different types. In particular, this is how we deal with handling conflicting events. How this works is we use a restricted type of transition systems that are called event structures. And conceptually, each transition in the event structure needs to be driven consistent updates. Part of this piece is that we have this locality for which we can guarantee that those programs can be implemented. So these are the two pieces of our approach. When updates happen with respect to events, and how to deal with conflicting events. So now that we have seen the consistency model that we want, let's look at how we can actually program in our approach. So as I said a minute ago, the netcat language can specify a single static configuration. What we want to do is extend this to allow specifying multiple configurations and also talk about updates between caused by events. So here's what the syntax of our language looks like. For those of you who are familiar with netcat, it should look pretty similar. The main difference is the one we have this global variable called state that we can line here and assignments to on the last line. So let's understand kind of how this works by trying to program this stateful firewall in stateful netcat. Stateful netcat program for that. The corresponds to the outgoing traffic. So basically an if statement that says if destination equals h4, so that's traffic, and port equals 1, then assign port equals 2, do some stuff in parentheses, port equals 4. So these are packets that are going across to the right. Inside the parentheses, we say a check for if state equals 0, then forward from switch 1 port 2 across to switch 4 port 3, and finally change the state to 1. Otherwise, if the state is 1, then just do the forwarding across the outgoing link and don't change the state. And so this last part represents the incoming link. And what happens is, you see at the end of the first line there, it checks for if the state is 1. And only at that point does it forward it across the incoming link. So that's the syntax of this language. Now we need to think about how can we define the semantics in terms of event-driven programs. So we can think of kind of the most basic approach is to have these simple transition systems where each of the each node in the transition system is a static configuration, and each of these edges is an event-driven consistent update between those two configurations. But there's a potential problem. This example is representing distributed events. So EN happens in New York, L happens on the other side of the ocean, and it could happen simultaneously. And in this case, the two devices of the current state, but it's actually not a problem here because once both of the devices know that both events have occurred, they will both be in the C3 configuration. So we view this as a resolvable type of conflict in our model. But let's look at this other example here. And in this one, we have a genuine problem because we really do need to know which of those events happened first. Is in the C5 configuration, and one is in the C6 configuration. There's no way to resolve this conflict without some kind of expensive coordination between those devices. So how do we and make this more clear? What we do in our paper is add additional structure to the transition systems. So rather than these basic transition systems, we have what's called structures which constrain very specifically how events can be related to other events. So we have two types of relationships between events. A certain event can happen after a set of events occurs. Note that by this turnstile relation. En can happen after no events have happened. Events can happen. The second compatibility, which says that two events can't have execution. Using this, we can kind of think about what are the sets of events that have occurred at each step of the program. And we can see that those event sets actually form. And it turns out that these two examples that I've shown here are exactly the transition systems from the previous slide, events on the nodes. Point. Okay, so this is the formalization, the semantics of stateful netcat programs. And the most important aspect of this is the condition that says incompatible events must occur. For example, on the right, EN and EL are so we rule out that program. So what is this locality bias? Programs which don't satisfy this locality, two things. They either need to buffer SDN, you don't want to do that, or they need to change state in some way that could end up unresolvable conflicts in the future. So that's not good. On the other hand, if we do satisfy the locality restriction, those programs, we can implement the programs with potential conflicts. So the formalization that is this lemma that we have in the paper that says, in general, you can't correctly implement that doesn't satisfy the locality condition unless you're willing to sacrifice availability of the network. Okay, so we talked about the syntax and semantic approach. So just let's look basically, just a basic example of how we compile. A compiler takes a stateful netcat program and it produces a network event structure. Essentially what happens is that we build a static configuration for each possible value of the state. And we do that using these tests on the state global variable. We also produce the event-driven edges, the event-driven transitions between these configurations, and that happens via this assignment. The details of this are laid out more clearly in the paper. So once you've compiled a stateful netcat program, now we want to run that in an actual SDN. So let's go back to this stateful firewall example. Hopefully it can be seen that the network event structure here, where the empty set can enable this event E, where E is arrival of an outgoing packet at S4. So there's only one event happening in the program, and it's the one that happens when a packet of the S4. So there are kind of this network event structure. The first one is when we have no event to this only outgoing configuration. And the second one is when we have a singleton set that causes the change. And that one maps to this configuration that has both. Okay, so how we actually go about running, we take advantage of the power of these stateful switches, and we store a set of currently heard about events on each of the switches. So initially, the switches don't know about any events, they just have an empty set. And let's look at this packet over to the right. Let's start it at H4 and send it into the network and see what happens. So when the packet enters the network, it's stamped with the current set that it sees at the edge switch. It's also stamped with the configuration that corresponds. So at all times in the future, that packet will be able to be routed according to that configuration. At this point, there's nothing more we can do. The C traffic across the incoming link, so that packet just. Now let's try a packet from H1 and send that into. So again, we stamp devices set, send that across the link. Now it's in this, since it's in the C configuration, it can go across that link. So at this point, we match this event E, because as I said, E is the arrival of an outgoing packet at that switch. So the event happens, and it gets added to the set on the switch as well as the set in the packet. And then the packet continues on. Okay, starting at H4 and send that one into the network. So at this point, we label with configuration C prime, because now S4 knows about E. Across that incoming link, because we're in the new configuration. S1 learns about that event and the packet. So if you implement any event-driven program in this way, guarantees that we want to provide, which are these update and also the event structure consistency. So now let's look at implementation of this and experiments. Netcat, Sable Netcat compiler, which and produces these event structures. So implementation with the switches. And then we wrote some scripts to deploy these programs in a mininet simulation running these modified OpenFlow switches. So just briefly, let's look at the performance of our system. So if you remember in the running example, each switch actually needs to know about all the possible configurations because it needs to know how to route packets that are tagged by those specific. So this is really inefficient in general. Each switch will need to have many rules. So what we do is try to use a rule reduction heuristic that shares rules across multiple configurations when possible. And we did some randomized configurations and found that we were able to reduce the total number of rules 2%. The other thing that we are customized OpenFlow implementation, switches, etc. And we did that with throughput stress tests in Mininet, and the performance was within 6% of our reference implementation. Okay, so the second thing that we did is where we wrote some real-world examples, and then we compared it with this of our program with the behavior of a different, we call this uncoordinated updates. So in that implementation, is sent to the controller, and the controller at some point later decides how to process the event and set up the new state that has changed in the network. So here's what happens with the uncoordinated, and for this example, the green line at the top corresponds to from H4 to H1, so trying to ping along the incoming edge, and the blue line is direction. So initially these pings are dropped, as you would expect, not allowing the incoming. And then we have some cause the state to change, and then these pings. The thing to note is that in the incorrect, some of these pings along the blue path dropped. And that is because the reply would need to traverse the incoming path. Incorrect implementation. So some of the responses to these outgoing pings end up getting dropped. We want, in the correct implementation, all of the outgoing pings work just fine. We also had another example where we had this learning switch. H4 wants to talk to H1. Initially, it doesn't know the network address of H1. So it has to flood traffic to all the devices in the network. Once H1 responds, it's able to learn the network address, and then it can send only on this green learned path. So those are the two states of the learning switch. In the incorrect implementation, we expect there only to be one packet flooded along these blue paths, and then the program should immediately switch after that to this learned path. In the incorrect implementation, again, 4 packets to be flooded before actually learning. In the correct implementation, there's only 1 packet. Also related work, stateful programming frameworks that don't have consistency guarantees, ones that have this atomic guarantee. And the thing that we provide is this new consistency model. It's about between allowing correct byte and also not sacrificing availability. And the two things are this event-driven consistent update and event structure consistency. A programming language and compiler for demonstrating actual usability via. Thanks.
This is really cool work. It seems like a much nicer than what sort of have experience doing in Netcat before. Though it seems like in your state variables, you're only storing constants or arrays. I wasn't sure of your notation. So I'm curious, do you think it can be generalized to sort of other kinds of data structures that, you know, hash tables and the things we're using while programming?
Yep, so that's a great question. So I think at this point, there's not an to generalize that. I think it would actually cause like explosion of the size of these programs, because basically you would have to add events for each possible value in the hash table, something like this. But you could think about a way of doing this with symbolic events. Actually investigated that.
Style of programming imply that I have to have all of the rules for all possible configurations and routers at all times?
Yes, so exactly. So that's one downside, is that you need to know all the rules, but the only way that we can attempting to share rules between configurations.
Do routers have enough space to store all this stuff? Is there any?
That is a good question. So in general, the space is really limited. So yeah, it may not be a great approach to use in networks where you have like many paths set up in the network.
So a follow-up question, sort of combining ours. So it seems like you're generating that event structure eagerly. Is there like a way to do it lazily, which might?
Yeah, that's a very good question. Yeah, we haven't actually thought of that one. That would be a good thing to try.